This is problem 16-35. A 300-pound force is applied to the end of a rope that is wrapped around the outside of a 6-foot diameter cable drum as shown in the figure below. Part A. If the 600-pound cable drum can be treated as a uniform cylinder, determine the angular acceleration of the cable drum and the time required to rotate the cable drum 3 revolutions. For part B, repeat part A if 300-pound force is replaced with a 300-pound block, as in the figure to the right. Okay, so we have done a problem similar to this, where we were given a force and we were also given a block that weighed the same as the force. And in that problem, we already saw that the results of the acceleration ended up being different for the disk. And I believe in that problem, we just calculated the angular acceleration of the disk. And even though the force was the same as the block, as far as how much force the block weighed, the acceleration ended up being different. Why was that? It's because the block had inertia and a force doesn't have inertia. So a block that weighs as much as a force will actually create a different effect. Now we're adding a new factor in that the disk has a rotational inertia. We're actually going to have to take into account the rotational inertia of the drum as well. And it's going to give us a third version of this kind of problem. So let's take a look at the math for this. As usual, let's start with a free body diagram. And we will have a connection at the center of the drum that creates reaction forces, A sub x, and then A sub y. We also have our weight. I'll just draw it up here. It doesn't matter where, just as long as the direction and location of application is consistent. And this is 600-pound drum. Okay, and then we have a tension. So to solve for this system, let's start with some of the moments about G. Because some of the forces in the X and some of the forces in the Y for the drum are kind of unhelpful. So think of it this way, like some of the forces in the X, we have A sub x, which is equal to the mass and the acceleration. The reaction force in the X direction is the only horizontal force. And the drum is not going to accelerate, so therefore 0. Okay, now let's look at some of the forces in the Y. We have basically A sub y, and we know in this part A that we have 300 pounds of tension. All right, so then minus 300, and then the weight of the drum is minus 600, and then equal to the mass times the acceleration in the x. So this is acceleration in the y, and the drum is not going to move. All right, well, then that tells us that A sub y is equal to 900 pounds. All right, great. So the question is asking us in part A to determine the angular acceleration of the cable drum and the time required to rotate the cable drum 3 revolutions. All right, well, let's see now what some of the moments about G will give us. So we have a center of gravity right here that's also at the anchor location at point A. So these 3 forces at point A will not be part of the moment about G calculation. The only force that matters is the tension that is 3 feet away from the center of gravity. All right, well, then 3 feet times T is equal to the rotational inertia about G times the angular acceleration. All right, well, what is the rotational inertia about G? Well, I sub G, this is a disk, like a thin disk or a thin cylinder. If we look at page 620, 621 that have the different objects, we'll see that it's 1/2 ml squared. Okay, what are these terms? Well, 1/2, and the mass is going to be the 600 divided by the acceleration due to gravity. And then the L squared is going to be the radius. So 3 squared. All right, this calculates out to be 83.85 slug feet squared. Don't worry too much about the units on this. That's the units for rotational inertia. All right, now they want us to find a rotational acceleration or an angular acceleration and a time for 3 revolutions. Well, the tension by itself is going to be equal to 300 pounds. So we have found IG, it's this value here, and we know the tension. It's given to us as 300 pounds. So therefore, we can just use the moment calculation and solve for the angular acceleration, and that's all they want us to find. So as far as I can tell right now, this equation and this equation weren't even necessary to answer the question that was asked. Just pointing that out. All right, well, if we solve for alpha, we get 10.73 radians per second squared. All right, now we need to find the time that it takes to do 3 revolutions. Well, how do we do that? Well, we can integrate the alpha into an omega. So that would end up being omega is equal to 10.73 t plus c, and this object starts at rest, so c is equal to 0. And then we integrate again, and we'll get a theta is equal to 5. Basically 37, kind of, I'm just rounding here, t squared. All right, well, then that is equal to how many times that we are going to go around, and we want 3 revolutions, 3 times 2 pi. So 2 pi is a revolution, and we want 3 of those. And then we solve for t. So t is equal to 1.874 seconds. All right, we've answered part A. All right, so all of this is just part A. Now, part B. Part B, we actually don't know this tension. We're not given the tension. So what are we given? We're given that there is a block that weighs 300 pounds. We can't just say, oh, well, therefore there's 300 pounds here. Because let's look at the free body diagram for the block real quick. The block is also going to have a tension. And since the string is inelastic, and I don't think they actually say it's inelastic, but at this point, we have learned to assume that strings are inelastic. I think it says in the preface of the book too, to assume inelastic strings or massless pulleys and things like that, unless otherwise specified. And then we have the weight. So at the center of gravity, we have a weight of 300 pounds. All right, now here's where the difference comes in. We have to do a free body diagram for the block. Well, the block's not going to move to the right or left, and the block is not going to rotate. It's just going to go up and down. So we can just do some of the forces in the y. All right, so some of the forces in the y are going to be the 300 pounds and the tension. So tension minus 300 pounds is equal to the mass, which the weight is 300 divided by 32.2, the acceleration due to gravity, and then the acceleration of the block in the y direction. Okay, so we basically have added an unknown, but we also added an equation. So since we were able to solve for the drum when there was just a known tension, now we have an unknown tension, but we've added an equation, and we need to see, can we solve this now? So technically, our 2 equations are going to be the moment about g and the sum of the forces in the y for the block. All right, how many actual unknowns do we have? Well, we do have an equation for the rotational inertia about g, and we have an unknown t, and we have an unknown alpha, but now we also have an unknown ay. So how are we going to solve for this? Well, the amount of string that is coming out of the drum is going to be equal to the drum's rotation converted from angular to linear. In other words, if I was to take the drum's radius, let's say this is point A on the drum, and then here's the radius of the drum. So this is the curved surface of one side of the drum. The motion in the downward direction is the conversion of radius times whatever rotation we care about. It could be the omega, it could be the alpha. Okay, so in this case, we want don't forget what we're looking for, an acceleration. So the acceleration linearly going downward is your ay. To get that value, we need to know r times alpha. Okay, so that means that ay can be written in terms of the known radius times alpha, and alpha is already an unknown over here. So let's rewrite some of the forces in the y. Tension minus 300 is equal to 300 over 32.2, and then the ay is now going to be r alpha. Okay. By the way, because I wrote my ay positive, I'm assuming that the acceleration is going up. And we know the block is going down. So expect the answer to be negative. Just FYI. Okay, now we have basically two equations, two unknowns. The two unknowns are the tension and alpha. Our two equations are some of the most about g and some of the forces in the y, just to recap. So we can solve. Well, the tension is equal to 150 pounds, and the alpha is equal to 5.37 radians per second squared. All right, and then they want us to find the time. It's the same process, so try it out, but the answer is 2.65 seconds. Now, what I'd like to point out is, why is the tension lower when the block is actually 300 pounds? And why is the acceleration changing? Well, the acceleration is probably a bit more obvious in that, well, the tension's lower. So the cylinder is feeling less force from the rope or the cable, and therefore would accelerate the drum at half of the value. Okay, that's probably, hopefully, pretty obvious. But why did the tension go down? Well, it's because of the inertia of the block. The inertia of the block has actually not allowed the cable to impart as strong of an acceleration because the block itself, the block's momentum resists a change in motion. It's just how physics works. And if this is hard to comprehend, well, you're in the same ballpark as me. But it doesn't make it not true. So this was one of the situations from my personal experience that not being able to comprehend, but seeing that the math worked out, and you could do experiments to verify these behaviors, caused me to rethink how I know stuff works. Sometimes I use intuition to verify my math, but every once in a while, I use the math to recalibrate my intuition. And this is one of these situations where I have to trust the math. And I could also, like I just said, trust an experiment to verify my math. And then that allows me to kind of reassess how I perceive the world, to be more accurate to reality and less about my gut instinct. And this is one of these situations where my gut, me personally, my gut does not do a good job of telling me what is actually happening. And the math is helping me recalibrate to a better, a more close to reality perception of what's going on.